Okay, this will be the lecture for chapter 11. We'll be talking about how all matter is made up of atoms, and it's going to be kind of important to take away, and we'll be talking about atoms a lot in the next couple of chapters and in Physics 102. So kind of where we're going to go is we're going to kind of follow the path as people figure out what atoms are as we know them today, and we'll talk about some characteristics and their structure. Talk about how atoms can make up elements, and there's something called a periodic table of elements, and if you haven't seen one in chemistry, you'll definitely see one here. Talk a little bit about the relative sizes of atoms, and I'll talk about how we can have different flavors of atoms or elements. And I'll talk about how atoms can join together to form compounds and the difference between compounds and mixtures, and I'll talk about how atoms can join together and form molecules. Now, people have always wondered, what makes up matter, and Aristotle, this poor fella, I keep on coming back to him saying he was wrong. He thought that matter was made up of the four elements, earth, air, fire, and water, but that's not entirely correct, actually, not even a little bit. The ancient Greeks were kind of thinking, well, what if I had a boulder, and I cut it in half, and then I had half of a boulder, so I had a big rock, and then I cut that in half, and so I had a quarter of a boulder, so I had a rock. Can make it smaller, make it a stone, grind it into sand, make something smaller than sand, cut it. The question is there a limit? And they said yes, there is something really small and solid and round, and we're going to call that an atom and say we cannot split that anymore. And that theory wasn't, the most highly regarded, but about the 1800s, there was a revival of this theory of an atom by this school teacher by the name of John Dalton. The big problem, of course, is we can't really see atoms. They're really small, and by really small, I mean really, really small. So it's hard to convince someone that something exists if you can't actually see it. And in the 1820s, a botanist, Robert Brown, was actually looking at some pollen in a petri dish, and what he kind of noticed was that his pollen kind of got bumped in this direction, that direction, this direction, and it kind of traced out this thing that now we call a random walk. And what he kind of theorized is it was sitting in water, and water is made up of atoms, so I've kind of drawn them. This is definitely not to scale. And these atoms were constantly in motion and bumping into his piece of pollen and essentially kind of pushing it on this random walk. And later this theory was confirmed by Einstein. Of course, everyone believes him. So there's just some basic characteristics of atoms is they're incredibly tiny, very, very, very tiny. I'm talking 10 to the minus 10th meters across, and that's about 1,000,000 times thinner than a piece of hair. Very, very, very numerous because they're so small. They have to be very numerous. If you're curious about how many atoms make up your human body, it can be roughly 10 to the 27th atoms, and yes, that is a 10 followed by 27 zeros. These guys are perpetually in motion, so they're constantly moving and bumping into things, and they're also ageless. The atoms that are around today were around when the dinosaurs roamed the earth, and they are the same atoms that were around when the Big Bang happened. You may be saying to yourself, wait a minute, Dr. Rogers, I know if I go ahead and I take a log and I set this bad boy on fire, then at the end of the day I'm not left with a log. And in some sense you are correct. You have changed kind of the chemical of that wood from being wood into being something else. You turned it into ash and smoke and a whole bunch of other things. So you've definitely broken some chemical bonds and released some energy, but the atoms themselves are the same. It's just they're joined together a little bit differently. Now, what makes up an atom? It turns out you can actually split an atom into even smaller pieces. You can split it up into 3 pieces. There's going to be made up of protons, there's going to be neutrons, and there's going to be electrons. And actually you can split these guys into even smaller things, but don't you worry about that for the purposes of this class. Now, some interesting things about protons, neutrons, and electrons is these protons and neutrons kind of join together, and they're going to form what's called the nucleus, and that's going to be kind of the center of an atom. and then these electrons are going to orbit it. So you kind of think of this being the sun, and this being this electron being Earth, and it's kind of orbiting it just like that. And something about these guys is protons are going to have a positive charge, neutrons are going to have no charge, and electrons are going to have a negative charge. But in general, atoms are going to be electrically neutral. And what that means is if we have two protons in the center, there's going to be two positive charges. We're in general going to have two electrons kind of orbiting it, making it electrically neutral. Two positives, two negatives, they're going to cancel each other out. Now, I want to talk a little bit about this nucleus. This nucleus is extremely small, 10 to the minus 15th meters. Now, you may be saying to yourself, wait a minute, Dr. Rogers, I know on the previous slide you said 10 to the minus 10 meters. When I said that, I was talking about this distance right there. So the size of the atom is dictated by the electrons. The nucleus is really, really, really small inside of this guy. And exactly how small, if you had a football stadium and you said that that's going to be, my atom, then if I went looking for this nucleus, it would be the size of a marble inside of that football stadium. So it's going to be really, really, really small. Now, most of the mass in an atom is going to come from the protons and the neutrons. Those guys are about 1,000 times heavier than the electrons. So it contains, most of the mass is located in this thing called the nucleus, which is again made up of protons and neutrons, and they're made up of about 1 atomic mass unit each, which is about 10 to the minus 27 kilograms. And these things called electrons essentially balance out the charge, and they exist in these things called shells, which is kind of a fancy word for saying orbits, and I'll talk about them in just a little bit. Now, you may be thinking to yourself, wait a minute, if I know that this is 10 to the minus 10, and this is 10 to the minus 15, then you might be saying to yourself, wow, look at all this empty space. Most of what we think of to be solid is actually empty, and you would be entirely right to say that. Now, it's the nucleus, or actually the number of protons, that tell us what an element is, and that's called the atomic number. So the number of protons dictate the element, and it's going to be the number of protons plus the number of neutrons that's going to give us most of the mass. So we have this thing defined to be the atomic mass number, which is really just going to be the number of protons plus the number of neutrons. Now, let's just kind of think about carbon for a second. The most common flavor of carbon is going to have 6 protons and 6 neutrons. So the atomic mass number would be 6 plus 6, or 12. So very frequently, this is kind of written as a C, which stands for carbon. The 12 is going to be the atomic mass number, and this 6 right here is going to tend to be the number of protons. And again, it's the number of protons that dictate what an element is. So for example, hydrogen is going to have no neutrons, 1 proton, and it's going to have an atomic mass number of 1. Helium is going to have 2 protons, so that guy right there, and it's actually going to have 2 neutrons, so it's going to have an atomic mass number of 4. So again, number of protons dictate what it is. Number of protons and neutrons dictate the atomic mass number. Now, I just want to talk a little bit more about these electrons and their orbits, which are called shells. Here I've kind of drawn the simplest possible element, which is going to be hydrogen. And hydrogen has 1 proton in the middle, and it's got this electron that's kind of hanging around in this orbit. Again, it's going to be constantly in motion, and it's going to be electrically neutral, so 1 positive charge, 1 negative charge. And as I add another positive charge, now there are neutrons that are being added here, but let's ignore those for a little bit. Then I'm going to add a second electron, so now we're talking about helium, which is still going to be electrically neutral. Now, if I were to add a third positive charge, well, it turns out that there's a certain number of electrons that can live inside of these shells, so there's no more room in this orbit for a third electron, and so it's going to populate another orbit. So it's going to kind of populate an orbit out here, and it's going to kind of pop out right here, and that's actually going to make it a little bit bigger. So right here, when we pop out to the next orbit, we're talking about a much bigger a bigger sized atom. And one thing that kind of keeps the world going around is like charges are going to attract, opposites are going to repel. So what kind of pulls these electrons around their orbit is the fact that they're attracted to that positive charge. But if you take a look at this guy right here, well, this guy is negative and this guy is negative. So these guys are kind of repelled from each other. And as we add more and more and more shells, so as we add more electrons, once this guy fills up, then we're going to have to add more. And it's going to kind of, we're going to have forces like this and forces like that. Now, in chemistry, they care about the number of electrons in the shells. I don't really care so much about the number of electrons that can live in the shells, but I do want you to know that these electrons live in these discrete orbits. So let's just take a quick little confidence test for which one of these guys are incorrect. So atoms are smaller than the wavelength of visible light. I had it on the slide, but I forgot to mention it. The wavelength of visible light is 10 to the minus 9th meters, and atoms are going to be 10 to the minus 10th meters, so yes, they are smaller than visible light. They are mostly empty space, as is the solar system. You never think about that, so this one is definitely right. They're perpetually moving. They're kind of bouncing back and forth, and the electrons are rotating around, so that one. Atoms are manufactured in plants and in humans during pregnancy. This one is not correct. They are not manufactured. They are transformed from one form to the other. They're never created or manufactured. So this guy right here is the incorrect one.